Hi, everyone. This is Aaron Larson, executive editor of Power Magazine, and you're listening to the Power Podcast. On today's episode, I'm joined by Eric Williams. Eric is the Chief Operating Officer with TerraPower. So, Eric, thank you so much for coming on the program. Please tell a little bit about yourself and your background in TerraPower.
Great. Thank you, Aaron. Very happy to join you today on this podcast. I've recently become the Chief Operating Officer for TerraPower. I think that was about 3 weeks ago. And I've been really associated with the design, licensing, procurement, and construction of the Natrium Reactor here at TerraPower. I've been here for about 10 years. Before that, I really spent my whole career working on pressurized water reactors, starting out with the current operating fleet of PWRs, then moving into some new designs that involved larger PWRs, and then small modular reactors. And then now I'm at TerraPower working on advanced reactors.
That's really what I want to talk about is the TerraPower design and what makes it different from other plants that are already in operation and also from other advanced reactors that are currently under development. Can you talk a little bit about that?
Yeah, sure. We call it the Natrium Reactor because it is in a class of reactors we call sodium fast reactors. In fact, the natrium word is just the Latin word for sodium. So that's how we get the elemental symbol Na on the periodic table. Some people like to ask about that. And we call it a generation 4 reactor type. And if some of your listeners may not be familiar with the lingo there, generation 4 just means the most advanced class of reactors. We typically use non-water coolants for running the reactor, and these designs have a greatly increased level of safety, performance, and economics. And so the Natrium design hits all of those attributes, and I can kind of just briefly discuss some of those. So enhanced safety in natrium really comes from the use of a liquid metal coolant. So sodium is a liquid metal, so it looks like what you would imagine, a shiny liquid substance. It's not related to table salt or anything like that, although it just involves the element sodium. And so liquid metals are so excellent at transferring heat away from the reactor, both to exchange that heat into other systems to go generate the electricity, or to remove the heat in an emergency situation. And so for the natrium reactor, we can do that heat removal directly to air if we want to. So that provides a very robust safety case for the reactor. It also gets its safety from being able to run at low pressure. Essentially, the primary system is at atmospheric pressure, whereas current pressurized water reactors have to pressurize the system to keep the liquid from boiling, to keep it in a liquid state. Liquid metal sodium doesn't boil until about 800 to 900 degrees Celsius, and the reactor operates down at 500 degrees Celsius. So that can remain a liquid and still be at a very high temperature without having to pressurize it. So those are two of the biggest things that lead to the safety of the Natrium design. Then we also have performance benefits that come from this. And one of those is the ability to store the energy in the form of molten salt heat coming out of the nuclear island. And so that is really giving us the ability to provide basically a grid scale energy storage solution. And it really matches up well with the current needs of the modern electricity grid. Because as we know, our grid today is very dominated by intermittency with renewable energy in many locations. And there needs to be this solution that provides some grid balancing and load following. And the way we do that with Natrium is by running the nuclear island at a constant heat output and then storing the energy in the form of molten salt and then using that stored energy to basically drive the steam turbine and generate electricity. What that allows us to do is, take the reactor that's producing heat at a 345 megawatt electric equivalent and go and load follow with that up to 500 megawatts electric. And we don't have to do anything with the nuclear island or make any changes in the power level of the reactor because we're storing the energy and using that stored energy to drive the turbine. And so that gives us the ability to load follow at a very rapid rate. It's really only limited by how fast your turbine can ramp up and down. And so it's very competitive with combined cycle plants and coal plants that are used today for load following. So that gives us some extra performance benefits. And then we take that and also use that to get economic benefits, which is also one of the big expectations of these Generation 4 reactors is that they'll lead to solutions that address economics and lower the cost and provide more reliable schedules for nuclear deployments today. And so that's one of the exciting things about the design is that those same safety and performance benefits also drive economic benefits. And so one of them comes up by paying attention to the architecture of the plant. So since we're storing the energy, we can actually decouple the whole side of the plant that's used to generate electricity from the side of the plant where you have the nuclear reactor. That energy storage comes in the form of molten salt storage tanks. And because of that, there's a large buffer between where the turbine is generating the electricity and where the reactor is generating the heat so that you can provide a decoupled architecture of the plant. And so, what that allows us to do is make that entire side of the plant for the energy island and make it non safety related. And so, that side of the plant has nothing to do with keeping the reactor safe. And that means the NRC oversight doesn't have to apply to the energy island side of the plant. So, all of that equipment can be built to lower cost and different codes and standards. The other thing it lets us do is it lets, for the first time in a nuclear plant, the grid operator can actually dispatch electricity with the turbine without having to go back and change anything on the nuclear island. So that allows a different kind of integrating with the grid for a nuclear plant that hasn't been achieved yet in the US. So we're very excited about that, the safety, the performance, and the economics. And it really gives us the ability to have a predictable schedule, and construction will be complete in 2030.
It's really fascinating to me to understand how this reactor works and how you're utilizing this molten salt. And I think about it all works great while it's in operation and everything is in steady states and the molten salt is molten. What happens in an upset condition where you have to shut down and you don't have the salt being heated at that moment by the reactor? Everything kind of solidifies, and how do you get it back into operation under such a situation?
So molten salt is really good at holding on to heat. So that's its real benefit. It's a little bit harder to get the heat into the molten salt. So you end up with heat exchangers that have to be a little bit larger when you're transferring heat into molten salt. But once you get it hot, it tends to want to remain hot. So as far as the tanks of molten salt go, those will remain liquid for a very long period of time. We won't need to do any sort of heating or worry about solidification in these large tanks. But when you're talking about the piping that carry the molten salt through the various pieces of equipment that go to the steam generators for generating steam, we do have to pay attention to freezing in that part of the plant. And so there's something called heat tracing, which is applied onto the piping. And so it's a type of electrical heating element that's wrapped around your piping. And it's used in those cases where you do have longer outages and you need to keep the system hot and prevent it from freezing. And in fact, if you were in an extended outage, we have some non safety related diesel generators that can come on to supply the electricity to keep the heat tracing going before you can get the plant back up and running, and then you won't need it anymore. So that is one of the things we'll pay attention to in the design. And this whole design for the molten salt storage is something that's currently being used in concentrated solar plants today. So we use the same kind of equipment used in solar plants, the same kind of salt composition, and all that heat tracing and other equipment is really coming from the solar industry. The only thing we do is we do pay more attention to reliability because we're a nuclear power plant and we have really high expectations for our capacity factors. We're really paying attention and looking for any single point vulnerabilities that might exist on that energy island. And we're going to be applying some added reliability there that you probably wouldn't need in a solar plant.
Okay, so it's nice to know that this is proven technology that's in use in other places, and really you're just using it for a different purpose with nuclear power. So that's great to hear. The most exciting thing to me is the fact that TerraPower actually has a plant under construction in Kemmerer, Wyoming, at a retiring coal facility. This is a joint effort with the U.S. Department of Energy's Advanced Reactor Demonstration Project. Can you give us some updates on that, where the project stands, what the timeline looks like, and any key milestones that you're targeting along the way to actual completion?
Yeah, absolutely. We're really excited to be working in the state of Wyoming. It is just a outstanding state for developing any kind of energy project, including nuclear energy. The people in the community are really welcoming to us. The state legislators are always looking for ways to remove any obstacles and just explain to us, how to get the permits we need and everything. So the project has been going really well from that standpoint. And if you think of any big project like this, you can think of it in buckets like engineering, procurement, and construction. So that'll give me kind of a framework to update you on the status. So engineering, we're really at the peak of the engineering phase of the project right now. We completed our preliminary design milestone in March of this year. So that means we're in the detailed design, the final design stage. So this is our last iteration through the design. It's really about getting all of the components into fabrication. And the construction is really going to be starting to mobilize here soon. So, engineering wise, we're really at the peak. And we have over 1,000 people working on the project. So, this is a very large project right now across, TerraPower and our major partners, Bechtel and General Electric, as well as all of our different engineering services firms that help us. So it's really the peak for engineering. And then licensing is going on in parallel. And licensing has really hit some milestones lately. We had our construction permit application submitted to the Nuclear Regulatory Commission last year, and it's really ahead of schedule. So, was supposed to get our construction permit application at the end of 2026, and it's looking like that's going to be significantly earlier than that. So that's pretty exciting. That construction permit application allows us to begin construction on the nuclear side of the plant. But we can really start construction on the non-nuclear side of the plant anytime now. So we're trying to mobilize our way towards full construction here at the beginning of next year. In the procurement phase, last year was our focus to get all of the nuclear island under procurement, all of the major equipment on the nuclear island, which is really where you have the custom engineered pieces of equipment that sometimes have longer lead times. So we're basically under procurement now for the nuclear island, and we're getting close to starting the fabrication phase on a lot of that equipment. In fact, in a couple of weeks here, we're going to be ordering long lead material for the reactor vessel head. And that'll be a real big milestone for us in terms of starting that process and then doing it on other components as we move forward. And then those pieces of equipment will gradually start to move into fabrication. So that'll be a big change in the project. And like I said, construction is moving through various steps. We actually started construction a year ago, actually, last June. We broke ground and we started working on what we call the test and fill facility. It's a dual use facility that is really right next to the nuclear site. And it's a test facility that allows us to do full size prototype testing for some of the major equipment that's going to go into the Kemmerer Unit 1 plant. It also is a facility that holds the liquid sodium that is used to fill up the reactor initially before it starts up. So it's a test and fill facility. And we just completed the foundation work on the test and fill facility this month here. And so we'll be starting to erect the building and it'll be completed at the end of this year. So that's the first facility for construction that's coming online. The second one is going to be called the Kemmerer Training Center. And this facility will start to mobilize this month and we'll start to build the KTC. And this facility is going to hold a full scope simulator for the Natrium reactor. It's also going to have classrooms for training, a couple laboratories for some of the operation staff to work in. And it's also going to be a visitor center. So it's going to have an auditorium for having big meetings and taking visitors in as well. So those two buildings will both be under construction this year. And then, like I said, we're going to move into construction on the non-nuclear side of the plant early next year or at the end of this year if we can. And so that'll be, the molten salt storage tanks, the steam generators, the steam turbine, that whole side of the plant we use to generate the electricity. We can start that construction anytime now. So we're just getting the design more mature and ready to do that right now. And then as soon as we get our construction permit application, like I said, I think it's going to be earlier than end of next year, then we'll start to work on the nuclear island and we'll start to begin excavating the site to put the reactor vessel in, which is located below grade. So it has to begin with an excavation there. And getting the reactor vessel set is a key milestone for us. And all of that leads to getting our actual operating license issued and completing construction in 2030.
Well, the term ahead of schedule is not something you often hear associated with nuclear projects, so I am glad to hear that coming out of your lips. Another
Yeah.
question that I have is about the procurement. Were you able to procure most of the components from U.S. manufacturers, or have you had to use overseas companies for some of these components?
Yeah, it's been a bit of a mix. I would say it's mostly US companies until we get to the actual larger components like the reactor vessel and reactor vessel head. In that area, we had to go to more of an international supply chain. And the reason wasn't really because we couldn't make those components in the US. It was that the US suppliers weren't really able to meet the schedule. So, we went out for competitive bids on all of this equipment, and we evaluated each supplier's ability to meet the schedule, meet the cost, and also their ability to scale up for the future where we expect to deploy multiple reactors in parallel. So, all of those attributes were really being reviewed, and it turned out that we had to go international for some of the bigger components.
Mhm. I know a lot of the advanced reactors that are under development, including TerraPower's design, use high-assay low-enriched uranium or HALEU fuel. Can you talk a little bit about that? I know, some possible bottlenecks in the supply chain for that type of fuel. What's your strategy for securing a reliable fuel, and how critical is domestic production of HALEU to ensure a stable and sustainable supply chain?
Yeah, that's a very important part of getting a high performing and economic reactor system is to have a secure supply for the fuel that you need. Our reactor does use high assay, low enriched uranium. So it's got an enrichment level just under 20%. And that is, part of being a fast reactor and having a fuel cycle that involves high burnups and high performance expectations as well. We need the HALEU to start up the reactor. So, this domestic supply has been a challenge for us. We still are looking at domestic supply in all different areas, so multiple different avenues for that. We are part of the HALEU availability program that is run by the Department of Energy. So far, it does not look like that program is going to deliver HALEU to us in time for the Wyoming plant to come online to give us our first core, or to give us the enough quantity to provide for the first core. We still are in discussions with Department of Energy on that, and that is not off the table. There's various different solutions that could come to bear through that program that would give us what we need. But right now, it doesn't look like that's going to meet the schedule. So we've had to turn to other options. We are also investing in other U.S. sources. So even after we deliver the Wyoming plant, we know we're going to need multiple sources of fuel. And so we continue to invest in U.S. domestic suppliers as well.
Mhm.
But it also looks like going directly to them under a commercial contract is not possible to meet the schedule. So then Finally, we went and looked outside the United States, and we recently did a go under contract with a company called ASP Isotopes. They have U.S. operations, and they also have plants in South Africa where they can make enough HALEU to supply the first core for Kemmerer Unit 1 and also for future cores. And so we are working with them, and they can meet our schedule for Kemmerer Unit 1. And so that is our primary, schedule compliant source of fuel right now is through ASP Isotopes. They also have different technologies that they're trying to advance that could also one day lead to a much more economic and a better schedule for supplying fuel in the future. So we're also working with them both on the short term and also long term solutions. And then finally, there's another aspect to the fuel specific to natrium in that once you have the high assay low enriched uranium, then you also have to metallize it because we use metallic fuel for natrium. So there's another step in there. And we are working domestically here with a company called Framatome to stand up a metallization plant. That'll be actually out here in Richland, Washington. And they're already producing demonstration batches using their metallization process. So we're really excited with the work that they've been doing. So that's kind of covers the whole supply chain, both kind of near term and longer term.
And I know you've gotten support, obviously, from the Department of Energy, and you've mentioned Bechtel and GE. Who else is involved that would be super important to getting this project completed?
Yeah, I mean the number one partnership is the federal government. So the public-private partnership is pretty key for these first of a kind projects that involve some initial development work that goes along with the deployment level work, I would say. So the U.S. government helps us a lot, and through their help, we also have access to the national labs. So I would say national labs are another big partnership that we have, and we've been working with them since long before the Natrium project started. TerraPower's been around since 2008, and I think, in our first days, even we were collaborating with Idaho National Lab, Argonne National Lab, Pacific Northwest National Lab. So the National Lab network is certainly a key partnership for us. And then when it comes to procurements, I think we also look to certain suppliers to be key partners, especially when it comes to not just delivering equipment under a supply contract for Kemmerer Unit 1, but also they become partners when they start to invest and take certain risks of their own in terms of being able to scale up for future deployments. And so we've signed over a dozen domestic supply chain agreements with these suppliers, and we're always looking for more. And so, if a partner like that is willing to work with us, maybe to increase the capacity for their manufacturing process and get ready for future deployments, that those are key partnerships for us. And so, what we look for in partnerships is really another entity that's willing to take a little bit of risk with us, maybe to scale up or maybe to invest in a faster process of their own, and then to have that ability to scale in the future when we need them to.
And it sounds like everything is moving along quite rapidly and successfully. What has you most optimistic about the future for this advanced design, and what are your biggest concerns at this point going forward? What could slow you down?
Yeah, there's a lot of things to be optimistic about these days. It's really a great time to be in the nuclear industry. And a lot of these things that I'll mention that make me optimistic, they weren't here when I started at TerraPower 10 years ago. So they've really come about just in the last, 5 to 8 years, I would say. But one of the things that makes me optimistic is the modern approach to regulation. The Nuclear Regulatory Commission, I feel like, has really listened to the requests from Congress and the White House to modernize their regulations. We now have a process we call the Licensing Modernization Program, which takes a risk informed view towards all of the equipment in the plant and whether it's providing a safety function or a backup to a safety function or no safety function. And so that's really given us the ability to make economic improvements to the plant and really gives us a good language to speak to the regulator that I think improves the whole regulatory approval process from all sides. So that makes me really optimistic that, schedules will be able to be achieved and it's playing out. I mean, with the NRC being ahead of schedule, really kind of demonstrates that the benefits of that. The second area is really the whole realm of digital solutions that are now available for nuclear power plant design and deployment. These things didn't exist, for the current fleet of reactors that we have here in the country. So it's great to see these things available. They provide ability to automate a lot of our design work. In fact, sodium fast reactors were a bit held back historically because of the lack of high performance computing solutions. And so one of the first things TerraPower did is invest in a large high performance computing cluster to go through all of the core design iterations you have to do for this design. It also plays into configuration management. So I'm excited to see these digital tools able to fully approach the whole configuration management system from a digital perspective all the way through construction. So you can think of digital construction work packages and construction personnel carrying around iPads that give them access to the configuration management system directly and communication directly back to the home office for any kind of design changes in the field. So that's pretty exciting. It also comes up in cloud computing. We're actually able to use cloud computing for running a lot of our design analyses and meeting our schedules better. And then finally, artificial intelligence is another one that, could provide solutions like digital twins that provide, real-time data for us to look at as the plant is operating and allow us to improve aspects of the plant. So all of the digital solutions are really exciting. And I guess I'll throw in a couple things that are concerning to me. Really, one of them is the supply chain. I've talked about how we have gone out to an international supply chain and we're getting our procurements under contract, and that's going really well. But as we get closer to fabrication, I just really worry that a lot of the supply chain is new to making these pieces of equipment. And so we really have to work closely with each one and really do our best in the design phase to make their job easy. And so that is kind of a challenge for a first of a kind design. But we're definitely taking that on and putting some of our engineers in the manufacturer's plant to be able to work closely with them, understand whatever issues they're facing, and be able to communicate very quickly. So, all that being said, we're still pretty optimistic. In fact, TerraPower is so optimistic that we're working on two different advanced reactor designs. We haven't talked about the molten chloride fast reactor, but we also have that design being developed here at TerraPower, and it also shows some great promise to be even more economic than the Natrium reactor in areas that are very difficult to decarbonize in terms of like maritime applications and high temperature industrial applications. So we're pretty optimistic about advanced reactors here.
Very interesting. And you obviously have talked about some of the things that have happened over the past decade. As you look forward to the next decade, do you see, success at Kemmerer potentially leading to much bigger things, a bevy of orders from potential customers that could be interested in your design? And who are those target users? Are you expecting to sell these to utilities, or can you sell them on a smaller scale to perhaps industrial and manufacturing companies, or to the military or data center operators, or who are you really targeting, or who do you think will really benefit from this design?
Yeah, really all of the above. But one of the things that we repeat often here at TerraPower is we try to remind ourselves that All of those future opportunities really depend on executing the demonstration reactor in Wyoming. So we really try to focus on that because that retires a lot of the risk that those future and opens up those future opportunities for us. So that being said, we are looking to scale across the U.S. As well as internationally. And I think sometimes the users are the ones that come to the table first, such as data centers and manufacturers in heavy industry. Those sorts of users come to us first, and we bring the utility along second. And sometimes the utility comes first, and they have a number of users in their network that involve some of the same people. So it's really interesting in the market today that you sometimes are having these conversations across, multiple different angles, directly with the users or directly with the utilities. And Natrium has the ability to produce electricity or produce heat in the form of steam or produce both electricity and steam. So that energy island architecture really opens up so many different kinds of use cases that we end up talking with all of these different potential customers for the product. And it really is a real open discussion with all of that flexibility available.
And you noted how it's a great time to be involved in the nuclear industry, but we haven't had that nuclear pipeline for a long time. So, how are you approaching the workforce development issue and getting people involved and trained and up to speed on what you need to build these plants and operate these plants in the long term?
Yeah, absolutely. So, I talked about manufacturing scale up, but there's also the deployment scale up, which gets into this workforce question. And one of the good things is that that was really an area that the state of Wyoming helped us with quite a bit from the very early days of the Natrium project and putting us in touch with the community and with all the different colleges and universities that could deliver workforce talent for the Natrium reactor. It's also a unique aspect of our design that most of the plant is non-nuclear. So having that separation between the energy island and the nuclear island, it really minimizes the part of the plant that requires nuclear specific talent. And it opens up a larger part of the plant to people that don't come from nuclear backgrounds. And so that's really been one of the great aspects to it. And then locating it close to a retiring coal facility in Wyoming means that a lot of that engineering and workforce talent from the coal plant can transition over to the energy island part of Natrium. And maybe that's where they begin, but maybe down the road, they get enough skills there that they can then train up and go work on the nuclear island. So there's definitely a unique architecture and design of the plant that allows more of that non nuclear talent to come in and help with the work. Also, Wyoming is a community with an incredibly high, I'd say, energy IQ, if you will. So they know about this. They've been helping us find solutions for this from the earliest days of the project. The Wyoming community really knows what it takes to produce energy. So we have a lot of relationships with the universities and colleges, even community colleges that can, produce welders and people that can help on the construction for Natrium. I actually work a lot with the University of Wyoming. We try to every year provide internships for them to actually work with TerraPower and get to know the technology, and then go spread the word back on the campus so that we can get people interested in working with us from the state. So, that's really one of the very enjoyable parts of my work is to see how the benefits of this plant coming online don't have to wait until the plant starts to produce electricity. They can start actually now by providing jobs for these people to transition to.
Well, that's great. This has been a really interesting conversation, Eric. Is there anything that I haven't asked about that you feel would be important to mention before we wrap up the podcast?
No, I just think I'm very happy that you invited me and I had the opportunity to talk about the great work that we're doing. I'd say one thing to add is that TerraPower has these two advanced reactor designs, but we also have another program that is in the operational phase already, and that is to produce medical isotopes. So it's been a really interesting part of my journey here that the work that we were doing on advanced reactors in terms of radiochemists coming up with new fuels for the molten chloride fast reactor led to this idea to take weapons waste essentially from Oak Ridge National Laboratory and find a way to create medical isotopes from it that are used to treat cancers. And so I'm excited that we have these advanced reactors, but we also have this project where material is coming out of our lab today and it's going into human trials and people are benefiting from that. And so it's just an amazing time to be in nuclear innovation.
Indeed, it is. So, again, for listeners, I've been speaking with Eric Williams, CEO of TerraPower. Thanks again for your time and insight, Eric. It's been a pleasure speaking with you.
Thank you, Aaron.